In this podcast, we'll continue our high-level look at stellar processes by looking at what kind of fusion happens when we've left the main sequence, and then a quick recap on the different types of supernovae that we can observe. Here are the understandings and skills that we have to apply. We'll review these at the end of the podcast. So previously we looked at the two different processes, the proton-proton cycle and the CNO cycle, which operate on the main sequence depending on the luminosity and mass of a star. But after a while, the hydrogen has been mostly burned that's available, is mostly burned to form helium, and we start to burn helium. Okay. Now, how does this happen? Well, there's an important thing you need to know called the alpha process. The alpha process happens when two helium nuclei combine to form beryllium-8. Now, beryllium-8 is very, very unstable, but it can have carbon-12 if before it has time to decay, another helium hits it. That's how carbon-12 is formed to help catalyze the CNO reaction, the CNO cycle in high-mass stars. That alpha process doesn't just stop at carbon-12, though. It can go beyond carbon-12. And in higher mass stars, then those alpha processes can build up. The trick is that it has to happen only in areas with large amounts of helium flux, because many of these want to actually decay and aren't very stable. But as long as the helium keeps on hitting before it has a chance to decay, then eventually this process can take you all the way up to iron. However, outside of the alpha process, you have a main fusion going on. So helium burns to form carbon. Don't forget, by burning here, we're just talking the astronomer's term for fusion reactions. Carbon itself, if you can manage to get your core to a temperature of 5 times 10 to the 8 K, which only happens if you can be at least 4 solar masses, then there's a variety of carbon reactions where carbon hits carbon and makes neon or sodium or magnesium. So you have a neon core builds up. After that carbon in the core starts to become exhausted, the carbon moves off to form a shell, and you have neon, and the core, if it can, it will collapse, and if it can collapse and reach a temperature greater than 1.2 billion Kelvin, then there's a variety of neon burning reactions that will take place, forming oxygen, magnesium, etc. And then, if you can, you have this oxygen magnesium core formed, and then if possible, the oxygen magnesium core will collapse, and if it can reach a temperature of 1.5 billion Kelvin, then again you have a whole variety of oxygen burning reactions that can take place, forming silicon or sulfur or phosphorus. These successive stages take less and less time, with neon burning just a few years, oxygen burning 6 months, maybe 1 year at the maximum, and then you get to the silicon burning. So most of your core at this point will now be silicon, and silicon burning happens again by the alpha process that we just looked at. So only the alpha process applies. Oxygen burning is the last stage which doesn't use the alpha process. So now you've got large amounts of helium flux. Helium reactions. Helium is actually being created in the core at this point. It's being created by photodisintegration. Some of the heavier nuclei get hit by the photons, but the photons have so much energy that they're able to break apart those nuclei in a sort of reverse fusion process, which releases some of the heliums which can then get used inside the silicon burning process. So you're not expected to remember all these reactions. You are expected to kind of remember that carbon burns basically to form neon and a few bits of other stuff, neon to oxygen and oxygen to silicon. So that's everything up to iron. And iron is the endpoint for nuclear fusion. normally because of its binding energy per nucleon. So how is any element in the universe heavier than iron produced? Well, there's two main methods, S process and the R process. And both of them basically use a method called neutron capture. The idea being that neutrons occasionally will hit a nucleus and occasionally will stick. This is a lot easier than, say, a proton doing it. A proton can't just hit a nucleus because of Coulomb repulsion, because they're both positively charged. But neutrons, under the right circumstances, can. They don't have a charge, so they can just kind of wander up to the nucleus. It's a rare event. It requires a significant neutron flux. But it does happen. If you have a seed, if you already have some heavy elements such as iron, and you have some neutrons wandering around, then as long as you're prepared to wait thousands of years, which it does in the S process, then it can happen. Okay, so this chart illustrates it quite nicely. Suppose you got some silver 109. Along comes a neutron, and you get silver 110, but silver 110 instantly decays by the beta decay to cadmium 110. Cadmium 110 will absorb a neutron and form cadmium 111, which will absorb a neutron at some point and form cadmium 112, which will absorb a neutron at some point and form cadmium 113, which will absorb a neutron at some point and form cadmium 114, which will absorb a neutron at some point and form cadmium 115, but cadmium 115 is unstable, it decays by nuclear decay, we get to indium 115, which absorbs a neutron, which decays by beta decay to tin 116, etc., etc., etc. The important point in the slow process is that A, it takes a long time, and B, if there is an opportunity for beta decay, it will occur. So cadmium 111, 112, 113, 114, they don't they're fairly stable, so there's no beta decay involved. But as soon as you get cadmium 115, then there's beta decay. You've got no chance to make cadmium 116, for example, which is actually quite stable, because the process is so rare that the beta decay will for certain happen, or almost certainly happen, before another neutron has a chance to come along. So that is the slow process. As for slow, thousands of years per event. So it appears in the atmospheres of very large stars, asymptotic red giants, and that produces about, this process, the S process, about 50% of all elements heavier than iron are produced by the S process, if you look at the abundances. It does stop at bismuth. It cannot go above bismuth because it enters a sort of cycle. Bismuth absorbs a neutron, absorbs a neutron, which decays to something less, and then which decays to something less, and then because bismuth actually decays by alpha, so it decays off by alpha, and you build up to bismuth, and it decays by alpha, so you never get past bismuth. So what about the R process? If 50% of heavy nuclei are created in the S process, taking many thousands of years, the R process happens an event lasting about a second. And that's the core collapse and rebound of a type 2 supernova. When that happens, you've got an exceptionally high neutron flux. So neutron capture occurs, as we've previously described, it goes up by neutron. But before beta decay can occur, another neutron comes along. In fact, during the events, beta decay can't occur because it's a little bit like evaporation. There's nowhere for an electron to go to. All the nearby Fermi states are already occupied. So beta decay just cannot happen. So because it can't happen, or at least it can't happen immediately, and there's such a high neutron flux, such high numbers of neutrons, then heavy elements can be created. This doesn't require a seed nuclei. This can take even relatively light nuclei and build them up. And it can create anything up to plutonium. Well, theoretically, it could create beyond plutonium, but beyond plutonium, everything has such a short half-life that by the time it enters the interstellar medium and then gevids and collapses to form a new generation of stars, etc. It's all decayed away. Only plutonium, neptunium, uranium, really heavy elements, have half-lives long enough to move from being created in a supernova explosion to actually forming part of the makeup of a future solar system. But that chart, you can see there, does give a nice breakdown of the origins of different elements, from the hydrogen and helium formed in a Big Bang through to the extremely heavy radioactive elements which are only formed by us, man-made. Just to finish off, we have mentioned this when we looked at cosmology, but it's just worth a reminder, and it's specifically mentioned in the high-level stellar processes. We've talked about supernova. Before, we were just talking about supernova type then. But there are two types of supernova. Well, there's more than two, but the two main ones we need to know about are the 1A and the type 2. Type 1A and type 2. This photograph shows the brightest type 1A supernova that we have observed in the last 300 years. This is in the galaxy M82, which is a mere 110 million light years away, which is, is it 11 million light years? I think it's 11 million light years away, which is practically next door. And a type 1 supernova, type 1A supernova, is not formed from a collapsing core of a big star. Instead, a type 1 supernova is actually a white dwarf that is not alone, it's part of the stellar companion. Mass transfers onto the white dwarf. White dwarfs have a maximum mass of about 1.4 solar masses, known as the Chandrasekhar limit, which you should know about. But if a mass acting on a white dwarf, if it's got a companion star, then mass can fall onto it. Then just before it actually reaches the Chandrasekhar limit, the core gets hot enough for carbon fusion to occur. So in a really high mass star, carbon fusion occurs, but it's kind of contained by the mass of the star squeezing in on it. In a white dwarf, a significant fraction of a star suddenly fuses with nothing to contain it. So it explodes. Huge luminosity, spreads a lot of iron and nickel out into the universe. Doesn't leave behind a neutron star, doesn't leave behind a black hole, because the explosion basically rips apart the white dwarf star. So that's the type 1A supernova. And because type 1A supernova occur under very similar conditions, with having the same mass and the same circumstances, then the amount of energy they output is actually very predictable, which means their luminosity is very predictable, which means we can use them as standard candles, which we did to provide evidence for the accelerating universe that we looked at in the cosmology podcast. Type 2 supernova, by the way, is your standard collapsing core supernova that we've looked at behind. So this chart's quite nice. On type 1 supernova up the top, binary star system, white dwarf formed, red giant sucked onto white dwarf, and then it all goes pop. Type 2 supernova is a big star, collapsing core rebound, forms a shock wave, and again, a really big bang. Okay, so that finishes the stellar processes unit.